Yeah, and then just to round it up, you can use different base functions, of course, also. So piecewise aggregate approximations use box functions. Yeah, so each box the time series is partitioned into boxes. Each box has the same length and approximates the interval of the same length by the mean of the corresponding values within this interval. Yeah, so it's very similar to downsampling, using the mean as representative value. It still has a lower bounding property regarding the distance calculations, Euclidean distance, dynamic time warping. Time series now may have arbitrary length, of course, and it's good if there are repeated intervals. Then these downsampling things are good. Especially if they have repeated intervals with the same length, each having values with a similar amplitude. Then, of course, these box. So here is a long where there is no too much difference in the amplitude. So we can approximate that with these boxes, of course, much better with these middle mean values in the boxes, better than if we have a lot of up and down going on in a short time period. Yeah, adaptive piecewise constant approximation is an extension to PAA, to this one here, obviously, where the time intervals now, the boxes may have different time intervals. Yeah, so because in case of PAA we cannot account for different amounts of detail, and adaptive piecewise constant approximation (APCA) allows boxes of variable length. So each segment has now two values or two parameters, the mean and the length. Yeah, here in PAA we only have the mean because the length is always fixed. Now in APCA we additionally store the length because the length can be different for different boxes, but the idea is the same basically. And going a little bit more complex is PLA, piecewise linear approximation. Basically the same idea, but now not we don't extract the mean of the boxes, but we extract the height or the value at start and the value at the end, and of course the length, because from those three parameters we can compute the slope and stuff like that. Yeah. That is an even richer representation than before. Somehow the downside is two consecutive segments need not to be connected, as here also, because we have these jumps here, and the same holds true of course here. But it yields of course a richer approximation of the intervals. But again, of course, since it's richer, it requires more parameters, but that's somehow obvious, I would say. Yeah, so that was feature reduction, and next would be one example actually for an application-specific semantic feature extraction. Extremely application-specific. That's why we only represent one as just an example to give you an idea what kind of features could you somehow extract. Yeah, doesn't mean that exactly this semantic feature representation fits to your application. It's just an idea, just an example. Yeah. So the basic idea is in some applications only significant events, significant shapes, whatever, are defined by certain amplitudes. Yeah, are interesting. So far feature extraction only models certain properties of time intervals, but not of amplitude intervals. Yeah? So that was the basic idea of this approach here, which we published in the early years of whatever. The basic idea from applications was that, we have, for example, in environmental science, but also in medical diagnosis, maybe here for these heart rates, we have not time intervals that are interesting. We have amplitude spectra, which are amplitude intervals, which are interesting. Yeah. So if you ask a doctor, what are the interesting parts of such a heart rate, she or he will tell you that we are only looking at those parts where the heart rate is in between those two values here along the amplitude spectrum, not along the time. Yeah. So all that stuff above here is not relevant for example, our cardiac infarction. And also the stuff down here is not relevant. It's only relevant what happens in between those this red interval here. And this interval is made up or defined in terms of the amplitude spectrum and not in terms of the time spectrum. Yeah? And so far we only extracted features along the time spectrum. Now we want to extract features along the amplitude spectrum. Yeah? And the same holds true here, for example, for this environmental science application. Ozone concentration, which is dangerous above a given threshold of the amplitude spectrum, and below we don't care actually. So we are interested in when is the ozone concentration above a given threshold, in which intervals, time intervals. Yeah? So the model is very simple. We transformed the time series into sequences that are above a given threshold or below a given threshold. Yeah? And since above and below actually, well, we can just compute one of those two because the other one is redundant. So given a given threshold tau, we computed, or we transformed the time series. So this is the original time series here. We transformed the time series into a set of intervals, and the intervals represent those time intervals where the original time series is above this threshold here. So you see that here is the second one, here's the third one. Yeah. So the threshold based representation of this time series here, according to this threshold tau here, is the set of these three intervals here. And now we have a set of time series consisting of a set of sequences of intervals. Yeah? And we have to compare sequences of intervals now in order to look for similar or not similar time series. So in order to compute the similarity between time series, we want to look at the sequences of these intervals here. So how can we do that? Well, there are many different ways to do that. What we actually, well, don't go into details here too much. What we actually do is we take the sum of the minimum distances between two sequences of intervals. Yeah? So this is the sequence of intervals representing time series x. This is the sequence of intervals representing time series y. And we can just take the sum of the minimum distances between all the pairs of sequences of intervals, from the sequences. Yeah? And that can be computed by these two factors here, or two factors of a sum here. So we map all the intervals from the first sequence to the intervals of the second sequence. So this is the mapping from all the intervals from x to the intervals of y, and the other way around. Yeah? And then just sum everything up. Yeah? So we map everything from x to the best match of y, and we match everything from y to the best match of x. That's why it is the minimum here. That is the best match from x to y or from y to x. Yeah? That's the minimum here, and then we just sum that everything up. Yeah? So that is this so-called sum of minimum distance, and that can be used as a distance function for those time series here. Yeah? So that is just an example for application-specific features with a specific distance function, of course, to compare time series to compute distances here. Yeah, that was everything about time series we wanted to show you. Of course, there's much more, but yeah, this was just a kind of basic tools that you can use when you are mining or analyzing time series data.